Hi everyone, I'm Chris and welcome back to this machine learning course. In this lecture, we will consider decision trees step by step. First, in this section, the idea behind decision trees is introduced. The decision tree model and its application to classification tasks is presented. After that, we will learn how decision trees are fitted to data using the so-called Gini impurity measure. This impurity measure is applied in an optimization to find the best decision tree for a given training dataset. Finally, we will take a look at different hyperparameters of the decision tree algorithm. There are different types of algorithms which can be used for classification. An example is logistic regression. The idea is to modify the linear regression model with a logistic function. This S-shaped curve is fitted to training data. Then it is used to classify new data by its corresponding value of the logistic function. This model fitting and its application to new data is very similar to how regression models are used. This is why logistic regression is called a regression type of classification. A different approach for classification is used by support vector machines. Here, two different classes are separated geometrically by a boundary in the input space. For the standard linear support vector machine, this separating boundary has a linear shape. New data is classified according to this boundary. So in contrast to logistic regression, this is a more geometrically motivated approach for classification. In this lecture, we consider another geometric approach. This approach is called decision tree. Let's consider an example for a classification problem with multiple classes. Here, in the example on the right, we have two input variables, the independent variables x1 and x2. Further, we have three different classes, symbolized by light blue dots, blue stars, and dark blue circles. The idea of a decision tree is to successively break down the given training data into regions of data points of the same class. Therefore, the decision tree answers yes/no questions to the independent variables x1 and x2. For example, such a question can be: is the value of the variable x1 greater than 5 or not? This question splits the input space into two halves. The separating line is perpendicular to the coordinate axis. Further questions split the input space. If a region with data points of a single class is identified, new data in this region is classified according to this class. Let's go into the details of this example. We start with the entire given dataset, which is used as training data to build the decision tree. The first question was: is the value of the variable x1 greater than 5 or not? The answer to this question splits the feature space of the two independent input variables x1 and x2 into two parts. The half with x1 greater than 5 on the right and the half on the left of the splitting line. The decision tree structure with the splitting questions is sketched on the left. A question is called a split because it splits the data into two parts. The origin of a split with its data is called a node of the tree structure. This first node is also called the root node. Next, we consider the left half of our first split. These are data points with values less than or equal to 5 for x1. At this node, we choose another split at x2 is equal to 2 to separate the light blue dots and the blue stars. So the second question is, for all data with values less than or equal to 5 for x1, is the value for x2 greater than 2 or not? If a data point's x1 value is less than 5 and its x2 value is greater than 2, it belongs to the class of the light blue dots. If the data point's x1 value is less than or equal to 5 and x2 is less than or equal to 2, it belongs to the class of the blue stars. Next, we consider the right half of the first split. At this node, the data point's x1 value is greater than 5. We then ask the question, for all data with x1 greater than 5, is x2 greater than 3 or not? If so, we have only data with the class of the blue stars left. However, for the lower right area, where x1 is greater than 5 and x2 is less than or equal to 3, we need another split to separate the classes of the light blue dots and the dark blue circles. So we use another question. For all data with x1 greater than 5 and x2 less than or equal to 3, is x1 greater than 6 or not? If so, we have the light blue dots. If not, we have the dark blue circles. Note that nodes with no further split are called leaf nodes. These leaf nodes represent the rectangles in the input space and give the classification according to the class of the training dataset. Here we have the light blue dots, here the blue stars, and here the class of the dark blue circles. So, finally, we build a decision tree which splits the input variable space into rectangles where the given training data belongs to a specific class. Usually, it is not necessary to split until the training data is separated perfectly. We will go into the details in the section about hyperparameters of decision trees. But if you have multiple classes present at a leaf node, you can just classify according to the most frequent class. In the example here, the light blue dots. Both support vector machines as well as decision trees try to separate classes by splitting the input space. For the support vector machine, on the left, this is done by a continuous boundary which has a linear shape for the linear support vector machine. On the other side, the decision tree divides the input space by perpendicular splits. This example on the right is not linear separable, so the support vector machine without variable transformations cannot classify the data correctly. For a decision tree, this is no problem. Multiple splits at different locations can be used. The splits are usually perpendicular to the coordinate axis. This restriction limits the computational effort. On the left side, you can see an example where a non-perpendicular split would be more beneficial. Further, this example is linear separable. Therefore, here the support vector machine is perfect for this classification problem. In the next section, we will consider how to find the best split to build a decision tree. Section finished. If you liked this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.